Hello everyone. Today we are going to talk about MotionLM, multi-agent motion forecasting as language modeling. The motivation for this research is rooted in the need to improve interactive motion forecasting. The goal is to generate a sufficient number of samples to accurately represent the multimodal future distribution. This is crucial as existing approaches have shown limitations in effectively capturing the joint distribution over multimodal futures. Existing models face challenges in handling the complexity of multi-agent rollouts over discrete motion tokens. This complexity arises from the need to predict the movements of multiple agents simultaneously, each with their own unique behaviors and interactions. These models also struggle with latency issues, particularly in settings where quick response times are critical. This can be a significant drawback in real-world applications where decisions need to be made swiftly. Furthermore, some models may overfit or underfit depending on their parameter count. Overfitting occurs when a model learns the training data too well, to the point where it performs poorly on new, unseen data. On the other hand, underfitting happens when a model fails to learn enough from the training data, resulting in poor performance both on the training data and on new data. The limitations of these existing approaches highlight the need for a new method that can effectively handle multi-agent rollouts over discrete motion tokens, perform well in latency-critical settings, and strike a balance between overfitting and underfitting. This is the gap that the proposed method in this paper aims to fill. The authors of this paper are addressing the challenge of interactive motion forecasting. This problem is significant due to its potential applications in autonomous driving and robotics, where accurate prediction of future movements is crucial for safe and efficient operation. Previously, existing methods struggled to effectively capture the joint distribution over multimodal futures. This is due to the complexity of multi-agent rollouts over discrete motion tokens, which many models are not equipped to handle. Additionally, latency issues were common in these models, particularly in settings where quick response times are critical. Overfitting or underfitting was also a concern, as models with too many or too few parameters could not generalize well to new data. To overcome these issues, the authors introduced a new method that leverages multi-agent rollouts over discrete motion tokens. This approach generates a number of rollouts and clusters them down to a manageable number of modes for evaluation. The model was trained using the WOMD Interactive Prediction Challenge dataset, a rigorous benchmark for this task. The author's method resulted in new state-of-the-art performance on the WOMD Interactive Prediction Challenge, demonstrating its effectiveness. The model's performance improved as additional rollouts were utilized, indicating the potential for further enhancements with more data. The authors also explored distillation strategies from large autoregressive teachers, which could enable faster student models to be deployed in latency-critical settings. This is a key innovation that could significantly improve the practicality and usability of these models in real-world applications. In summary, the authors addressed significant problems with existing methods for interactive motion forecasting, introduced a novel approach that improves upon these methods, and achieved state-of-the-art results. Their work opens up new possibilities for future research and applications in this field. Section 1. Problem formulation and approach. The authors of this paper have formulated the problem of interactive motion forecasting as a task of generating a sufficient number of samples to represent the multimodal future distribution. They approach this problem by introducing a method that leverages multi-agent rollouts over discrete motion tokens. This method is unique in its ability to capture the joint distribution over multimodal futures, a task that existing models have struggled with. Section 2. Experimental design and methodology. The authors have designed their experiments to evaluate the performance of their proposed model using the WOMD Interactive Prediction Challenge dataset. They have used a number of rollouts and clustered them down to k=6 modes for evaluation. The performance of the model is evaluated across varying interactive attention frequencies and numbers of rollouts. The authors have also measured the model's inference latency on the latest generation of GPUs across different numbers of rollouts. Section 3. Improvements and innovations. The proposed model introduces several improvements and innovations over previous approaches. Firstly, it establishes new state-of-the-art performance on the WOMD Interactive Prediction Challenge. Secondly, the model's performance improves as additional rollouts are utilized. Thirdly, the model can be used in latency-critical settings with the exploration of distillation strategies from large autoregressive teachers. Lastly, the authors plan to leverage the trained model in model-based planning frameworks and learn amortized value functions from large datasets of scene rollouts in future work. Technical results: 1. The proposed model has achieved new state-of-the-art performance on the WOMD Interactive Prediction Challenge. This indicates that the model is highly effective in forecasting interactive motion. 2. In terms of marginal motion prediction, the model ranks second, less than 2% behind the score achieved by MTRA. This shows that the model is competitive with the current state of the art. 3. The model has shown a significant improvement in miss rate over all prior works, with a relative 9% reduction compared to the previous state of the art. This suggests that the model is more accurate in its predictions. 4. For interactive motion prediction, the model has achieved a 6% relative improvement in MAP and 3% relative improvement in miss rate over the previous top-scoring entry, JFP. This demonstrates the model's superior performance in predicting interactive motion. Ablation study and implications. 1. The model with 9 M-parameter replicas is used for the main results, with 27 M parameters overfitting and 300K underfitting. This suggests that the model's performance is sensitive to the number of parameters and that there is an optimal number of parameters for the best performance. 2. For the final leaderboard results, 512 rollouts per replica are used, although 32 rollouts are sufficient to surpass the previous top entry on joint map. This indicates that the model's performance improves with the use of additional rollouts, but there is a point of diminishing returns. Key insights: 1. The proposed model effectively captures the joint distribution over multimodal futures. This suggests that the model is capable of handling complex multi-agent interactions. 2. The model's performance improves with the use of additional rollouts. This indicates that the model benefits from having more data to work with. 3. The model can be used in latency-critical settings with the exploration of distillation strategies from large autoregressive teachers. This suggests that the model is not only effective but also efficient. 4. Future work includes leveraging the trained model in model-based planning frameworks and learning amortized value functions from large datasets of scene rollouts. This indicates potential areas for further improvement and application of the model. Key highlights of the paper: 1. Key insights. The paper presents a novel method for interactive motion forecasting that effectively captures the joint distribution over multimodal futures. The performance of the model improves with the use of additional rollouts. The model can also be used in latency-critical settings with the exploration of distillation strategies from large autoregressive teachers. 2. Key contribution. The paper introduces a new method leveraging multi-agent rollouts over discrete motion tokens. This method establishes a new state-of-the-art performance on the WOMD Interactive Prediction Challenge, surpassing previous models in both MAP and miss rate metrics. 3. Key idea. The central idea of the paper is to improve interactive motion forecasting by generating a sufficient number of samples to represent the multimodal future distribution. This is achieved by leveraging multi-agent rollouts over discrete motion tokens. 4. Key results. The proposed model achieves state-of-the-art results on the WOMD Interactive Prediction Challenge with a 6% relative improvement in MAP and 3% relative improvement in miss rate over the previous top-scoring entry. The model also showed a substantial improvement in miss rate over all prior works, with a relative 9% reduction compared to the previous state of the art. 5. Key conclusion. The paper concludes that the proposed model effectively improves interactive motion forecasting. Future work includes leveraging the trained model in model-based planning frameworks, learning amortized value functions from large datasets of scene rollouts, and exploring distillation strategies from large autoregressive teachers for deployment in latency-critical settings.